Greetings, STEM students. We get to move on today to looking at an additional way to solve a problem that we've already done. And so why am I having you solve the same problem twice? Well, there's a little comfort in that and knowing what you should get is the right answer. But what I want to do is give you a different way to think about solving the same problem. So, when we move forward in the future, you can look at using this approach to solve other problems that you haven't even thought of yet. So we are using the handout that is titled Solving Systems of Equations. Just to kind of recap, the front page looks like this. We are going to be on page 2 of that handout. So please take a minute right now, pause the video, and copy down these 2 equations that are written in red and green. And when you're done, unpause the video and we'll continue with the substitution method. So now you've had a chance to write down your equations. How does substitution work? Well, substitution is as simple as isolating a variable. And we did this skill first semester. All right, and then what we'll do is after you isolate the variable, like let's say we get x equals, and everything else is over here. You might have y's, you might have constants, but basically whatever you see right here on the other side of the isolated variable, we are going to substitute that expression. And when I say that, I'm going to just kind of point up here. Substitute that expression into the other equation. For, in this case, x, since that's what I solved for, we'll say for the variable that is isolated. Poor old lonely x is isolated by itself. So whenever we see an x in the other equation, we would replace it with the expression that's boxed off. So look to the left. In our 2 equations, we have 2 equations where y is already isolated. So what we can do is we can take the expression on either side of the y. In other words, I can take this and I can replace y with 75x plus 50. And if you remember back to our constant velocity vehicles, we did this method a lot of times. So this should look somewhat familiar. All right, so right here, instead of y, I'm going to replace y with 75x plus 50. And then I'm going to keep the other side of the equation identical. And so just to kind of highlight this here, this y and this expression are equivalent from the equation up above, but I'm replacing y with what it's equal to. So I can replace y with 75x plus 50, and then the other side of the equation stays the same, 50x plus 125. And now it's just a game of combining like terms to get the variable on one side and to get the constants on the other. So I just want to redraw that in here. Okay, so what ones are considered like terms? Well, let's see. We got an x right here and we got an x right here. So I can get those on one side. And then we have a constant here and a constant here. All right, now I'm a fan of working with positive numbers whenever possible. So this is really just an addition and subtraction game. So we want to get the terms on one side that have x's and the ones that don't have x's on the other side. So I'm going to subtract 50x from both sides of the equation. And we get 25x plus 50 on the left. And then on the right, the 50x's cancel and we're left with 125. Okay, now the 50 and 125 are like terms, so I want to move those to the side that doesn't contain the x's. So in order to get rid of plus 50, I gotta go minus 50. And I'm just gonna bring this over. So that cancels. So we're ending up with 25x equals 75, and x is equal to 3. That should look awfully familiar from the first page when we graphed this the other day. Flip over to the front page and you'll see x equals 3. All right. So it took 3 months. I'm going to include the units here. It took 3 months for the cell phones plans to balance out. And what we can do now is, now that we have our x, I'm going to come back up to either equation, it doesn't matter which one, and to figure out the y value, we're just going to replace x with the number we just got and evaluate that expression. So 75 times 3 is 225, plus 50 is 275. So our ordered pair will be identical to what we came up with when we graphed it. So if I write that as an ordered pair, we had 3 months for our x value, and the cost at that point was $375. So check the front of your handout. That should match up, and it should be perfectly aligned with the solution we came up with the other day. Okay, we're going to try this one more time on example 3. So turn the page to example 3, and if we're going to use substitution, I try to pick an equation that the x or the y is, somewhat by itself. Neither equation has x or y completely by itself. So I'm just going to take these two equations, and where it says use substitution, I'm going to copy these down. And then my second one is negative y minus 2x equals 4. All right, and so our goal is to get either x or y by itself. So I noticed this equation here. The y is not completely by itself, but it's pretty darn close. It's not a 1 in front of it, it's a negative 1. So let's think about isolating that yellow part. And in order to get rid of the yellow, or to get the yellow term by itself, I need to remove this guy. And the only way to remove him is to get him moved over to the other side so that that yellow term is by itself. So what's the opposite of subtracting 2x? We're going to add 2x to both sides of the equation. And that's going to cancel out the 2x on the left. So we get negative 1y. The 2x's cancel. And we're left with 4 plus 2x. Notice I didn't write that as 6x. They're not like terms, so you can't combine them. And then I'm just going to divide by a negative 1, which all that does is change your signs. So instead of positive 4, we get negative 4. Instead of positive 2x, we get negative 2x. So negative 4 minus 2x. All right, now y is by itself. So in this equation on the left, every time I see this y, I'm going to replace it with whatever I solved y to get over here. So I'm going to replace this with negative 4 minus 2x. Okay, so on my green equation, instead of writing y, I'm going to leave a big blank space, just like I did here. And in that blank space, this was y. I am going to replace that with what y is equal to, negative 4 minus 2x. And our whole goal now is to just combine like terms. And again, we did a lot of this first semester, so this should look pretty familiar. All right, so if I distribute the 2, we get negative 8 minus 4x plus 4x equals 8. Looks kind of interesting. So negative 8 Well, a negative 4x and a positive 4x cancel. Those end up equaling 0. So now, all my variables dropped out. Okay, well, negative 8 is equal to positive 8. That looks kind of weird. So, at this point, I know one of two things. I know I either made a calculation mistake, or I know, in this case, I know I did my math right. I know this is a false statement. All right, when this happens, we'll see this once we graph it. You should realize that a false statement basically means there is no solution. In other words, the lines are parallel. There's no way we're going to be able to find a spot on the graph where the lines intersect. All right, and so eventually you'll be graphing these, but I just wanted you to kind of see what happens when there is a no solution type of graph, or when you solve it algebraically and everything drops out. What does that mean? I don't want to say everything. When the x's drop out and the constants don't, we get a false statement. This basically means there's no solution. That means on the graph, they're never going to intersect. And that concludes your lesson for the day. We will practice this a little bit more when you come back to class. Have a good day.